This is our F1, and F2 equal to M2G minus tension, that is the force dragging it downward minus the tension opposing it. So if we consider the formula for force, F1 is equal to mass times acceleration, but here we are having what? M1 in terms of our F1, M1A. The acceleration will not carry any disparity because the acceleration in this mass is the same thing as the acceleration of what? This mass too. That is the rate at which M2 moves determines the rate at which M1 will also move. So they have the same acceleration. F2 equal to M2A. So this simply implies that M1A equal to T minus coefficient of friction times normal reactional force M1G. And we have M2A to also be equal to the weight M2G minus tension. So the tension is the same for both strings, so we can use this equation to find the tension. And mind you that the acceleration is equally the same. From here you can use a formula for acceleration, you can use a formula for tension. So as the case may be, but I prefer solving the equations simultaneously whenever I need to. So you can leave it this way and see that this is how you reduce this aspect. Yes. So this is it for a smooth plane. Then the case 5, the fifth case scenario is when we have an inclined plane connected by means of what? Pulley, frictionless pulley with another mass. Now, if we call this our M2, here our M1, everything that happens in the previous case still repeats itself. Here is our angle theta, our normal reactional force acting R, our weight W. Without being told, we know that here is going to be W sine of theta, and this side is W cosine of theta, our normal reactional force. So, why this angle is theta, as usual. Then, here is our M2G, the weight of this mass. Here is a tension T, another tension here, T. So, everything that holds in this first and this and fourth case holds here. Just that in this case, there's an angle. So, for this one hanging freely, nothing will change on the mass 2. That is for the second equation. You still have M2G minus tension to be equal to force, or force to be equal to this. Therefore, our M2A equal to M2G minus tension. You see that nothing happens to that equation. But for this equation, for the mass lying on the inclined plane, something will definitely change. Why? Because if you look at it now, our mass, total force, F, will be equal to, let's call it F1, will be equal to the tension trying to pull it minus the force trying to stop it. What is the force trying to stop it? In this case, we are going to have two types of force trying to what? Stop it. And the two forces are what? The force of friction and the force due to the weight. We have frictional force trying to what? Stop it, and the weight. So our frictional force now, Fr, minus the force of weight, W sine of theta. So F1 now, which is M1A, will now be equal to tension minus frictional force, mu R, minus W sine of theta. So that our M1A becomes tension minus coefficient of friction times normal frictional force, W cosine of theta, and our W is M1G cos theta minus W sine of theta, that is M1G sine of theta. You see the changes in this one. It's a bit change in this one. Yes. This is the net force. So that at the end of the day, you can factorize, do your mathematics, M1G is common, factor it out, and you will be left with something like this, T minus M1G into coefficient of friction cos theta minus sine theta. So that if the coefficient of friction is not given, then we decide to use tan theta to find our coefficient of friction. Yes. So that's that. So for an inclined plane, we should also know that the coefficient of friction mu is equal to tan theta. Why? Because if you look at this now, we can find our coefficient of friction from this aspect, where we say that F over R. If you have F over R, you're going to have what? W sine theta all over W cosine of theta. So that we're going to have coefficient of friction to be equal to tan theta if W strikes out. That's one thing you should also know about incline